Well, renewal works have begun on parts of MRT tracks with the worn-out ballast, gravel or coarse stone.
We began with a simple question about stones under steel, yet the journey revealed an engineered world hiding in plain sight, where jagged rocks quietly shoulder forces that would destroy concrete in days. The next time a train rushes past, remember the unseen system holding everything together, and let that curiosity lead you to the next story. The illusion of simplicity. To understand why railway tracks rest on what appears to be an untidy carpet of broken stones, we must first confront the deceptive simplicity of the scene itself, because nothing about those rocks is accidental. Travelers often assume that modern engineering would favor sleek concrete pads or seamless metal foundations, especially when supporting machines that haul entire cities' worth of weight across continents. Yet, the sight of those jagged gray fragments creates a quiet visual contradiction, as if an advanced transportation system had been placed on a surface borrowed from a construction site. This contrast draws attention to a deeper truth about railways. The most powerful solutions are not always the ones that look refined. This illusion becomes even more striking when you consider how trains behave in motion. A fully loaded freight engine does not glide along a track. It hammers it with shifting forces that pulse downward through every component. If the ground beneath were rigid, smooth, or uniform, those forces would travel straight into the earth, cracking whatever structure held the rails in place. Engineers learned early that nothing rigid could survive the repeated stresses of heavy locomotion. The stones remain because they achieve something no solid slab ever could, creating a foundation that absorbs chaos while maintaining order, even under extraordinary strain. The forces beneath a moving train. When a train begins to move, the elegant rhythm heard from a distance hides the violent physics unfolding beneath its wheels, where every rotation concentrates thousands of pounds of force onto an area no larger than a coin. This pressure transfers into the rails, which push it into the sleepers, which in turn deliver it directly to the ground. Without ballast, the earth below would deform instantly, sinking under the load and twisting the track into shapes too dangerous for any locomotive to navigate. Soil behaves unpredictably when stressed, shifting in patterns that no engineer can fully control, which is why rails laid directly on dirt would fail almost immediately once a modern freight train passed over them. Ballast intervenes by disrupting this downward collapse, transforming a narrow spike of force into a broad, dispersed field that the ground can absorb without losing stability. The angular edges of the stones interlock like an improvised masonry system, gripping one another tightly enough to act as a unified structure, while remaining flexible enough to shift microscopically under stress. This dual behavior allows the foundation to adapt to changing loads rather than break beneath them, creating a living, dynamic layer that constantly redistributes pressure. Ballast's three classic superpowers. Long before sensors revealed the deeper secrets of ballast, engineers relied on three essential behaviors that made these stones irreplaceable, beginning with their remarkable ability to manage water. Rainfall that lingers around tracks can transform firm ground into a slow-moving slurry, a process known as mud pumping, where every passing train forces pockets of water and soil upward until the structure collapses from within. Ballast prevents this by creating a porous network of voids that channel water downward and outward, allowing the sleepers to remain dry and the soil beneath to retain its strength. Without this constant drainage, even the best designed railways would deform after a single season of heavy storms. Equally vital is the ballast's ability to accommodate the natural expansion and contraction of steel. Rails grow subtly longer in the heat and contract during cold periods, generating hidden stresses that could buckle a rigid foundation into a dangerous curve. Ballast solves this by holding the sleepers firmly enough to maintain alignment while still permitting microscopic adjustments. This interplay between restraint and flexibility allows the track to breathe with the shifting seasons, protecting trains from misaligned rails and sudden structural failures. The third strength, often overlooked yet essential, lies in ballast's capacity to create an environment hostile to plant life. Roots that take hold along a railway can exert enough pressure to push sleepers aside or lift rails unevenly, compromising safety long before the problem becomes visible. The jagged stones form a nutrient-poor barrier that deprives seeds of soil, moisture retention, and sunlight, ensuring that vegetation remains sparse without the need for chemicals. Together, these three capabilities establish ballast as a guardian of reliability, preventing failures that would otherwise arise from water, temperature, and nature itself, and preparing the stage for the even more dramatic forces it must endure: ballast and micro-earthquakes. As railway systems grew heavier and more complex, researchers began asking how a bed of fractured stones could survive forces that routinely overwhelm engineered materials, leading geotechnical teams to install sensitive instruments beneath busy freight corridors. What they recorded challenged long-held assumptions, because the passage of a fully loaded train produced ground vibrations strong enough to register as micro-earthquakes. These were not destructive seismic events, yet they revealed that the interaction between steel, sleepers, and ballast generates pulses of energy far more intense than previously modeled. Instead of remaining rigid, the stones momentarily shifted under these impulses, sliding and tightening in patterns that resembled a controlled, temporary liquefaction. The discovery surprised engineers who had long viewed ballast purely as a static interlocking structure. High-speed sensors showed that when a heavy train approached, the ballast layer entered a dynamic phase in which individual stones adjusted to the surge of pressure before locking themselves back into place once the load passed. This ability to behave as both a fluid and a solid is extraordinarily rare in construction materials, and understanding it reframed ballast, not as a crude solution, but as a self-stabilizing system shaped by millions of load cycles. More importantly, the findings clarified why rigid concrete slabs often fail under similar conditions. When subjected to repeated shock waves, concrete develops microcracks that spread silently until the slab fractures, forcing long closures for repairs. Ballast, by contrast, dissipates energy through countless points of contact, preventing the accumulation of stress that would otherwise destroy the track bed. Railway maintenance teams, armed with this new understanding, began collaborating with seismologists to refine ballast depth, stone geometry, and maintenance schedules, ensuring that the system continues performing as an adaptive layer built to endure one of the harshest operational environments on Earth: the endless battle against time, weather, and wear. Even with its remarkable ability to absorb shock and reorganize itself after each passing train, ballast faces a slow but relentless erosion that transforms it over years of service. Every vibration generated by locomotives and freight cars causes the stones to grind against one another, dulling their sharp edges and producing fine dust that settles into the gaps responsible for drainage. As these voids begin to fill, water moves less freely through the layer, increasing the risk of saturation and weakening the soil that supports the entire structure. What once acted as a resilient, self-adjusting foundation gradually becomes a compacted mass, unable to perform the tasks that keep the railway stable. Weather compounds this challenge. Heavy rains accelerate the transport of dust deeper into the ballast, while freeze-thaw cycles widen any developing imperfections. The combination of mechanical wear and environmental intrusion means that no railway can rely on its ballast indefinitely, which is why enormous maintenance machines periodically appear along the tracks. These specialized ballast cleaners lift entire rail assemblies, sift the stones through vibrating screens, remove contaminated material, and return the usable fragments to their original position before adding new rock to restore the proper profile. The process resembles a medical procedure more than a simple repair, emphasizing how essential renewal is to the survival of the system. Through this continuous cycle of degradation and restoration, ballast maintains its ability to shoulder immense loads without compromising the safety or reliability of the railways it supports. The global debate. As railway technology expanded across continents, engineers began comparing traditional ballast systems with sleek concrete track beds used on some high-speed lines, creating a global discussion about which foundation would define the future of rail travel. Concrete appears, at first glance, to offer a modern alternative, providing a rigid surface that keeps rails perfectly aligned for trains traveling at extraordinary speeds. Yet this rigidity introduces vulnerabilities, because concrete cannot redistribute shock or adapt to subtle ground movements, meaning even small deformations can propagate into larger structural failures that require lengthy closures to repair. Countries such as Japan and France rely on these slabs for specialized high-speed corridors, but they reserve them for routes where precision outweighs adaptability. Most of the world continues to favor ballast because it remains cheaper to install, easier to repair, and better suited to the unpredictable terrains through which freight and passenger lines must operate. The debate ultimately highlights a broader truth. The survival of a railway depends not on the sophistication of its materials, but on how effectively its foundation responds to the forces trying to break it apart. The meaning beneath our feet. The stones supporting every railway line reveal how an unassuming material can shoulder responsibilities far greater than its appearance suggests, turning a scattered layer of rock into a system that protects trains from water, temperature, vibration, and the shifting ground below. Their quiet effectiveness reflects a deeper engineering philosophy in which strength comes not from rigidity, but from the ability to adapt gracefully to constant stress. By watching how ballast endures forces that would fracture more refined structures, we gain insight into the resilience required for the networks that connect modern life. What seems ordinary becomes a reminder of how stability often depends on elements we rarely notice. We began with a simple question about stones beneath steel, yet it uncovered a hidden architecture that keeps entire rail networks alive. The next time a train passes, remember the silent system working beneath your feet. And if you enjoy discovering the extraordinary inside the ordinary, subscribe, stay curious, and join us for the next journey.